Today's notes are on section 8-1 about potential energy. Okay, so the big definition of potential energy as we are studying it in physics is any kind of energy that can be stored, and it's this specific storage where the storage happens because these objects have been located in a certain way or configured in a certain way, and these objects have exert forces on each other, and so just the way that you locate the objects stores energy. And so, for instance, here we're seeing that we've paused a skater on a half pipe here, and they have energy because they are separated from planet Earth. And so we'll be talking about that more in a second. Okay, but your book is going to talk about these conservative and non-conservative forces. And what does that mean? So the type of force that is conservative, okay, is any kind of force where the work that is done by that force doesn't depend on the path that an object takes. So we don't care, what did the object travel up the mountain in this direction? Did it travel up the mountain in that direction? Doesn't matter. The work would be the same. So that's one way to tell that this is a conservative force. So that's a telltale sign. Oops, I skipped a slide. Okay. And then this idea is that also that a force is conservative if the net work done by that force around a closed path is 0. So you can see in this diagram here that would be true for gravity, because on the way up, this looks like a tomato here, this person threw the tomato, and so on the way up, the force of gravity did negative work to slow the tomato down. Okay, the force was opposite of the displacement because force is always down for gravity, but the tomato was going up, right? And so when we have that mismatch here, then negative work was done. Or another way to think of it was the tomato had kinetic energy at first, but then it stopped right here, so it lost its kinetic energy. And then on the way back down, gravity sped up the tomato, and so it added to the kinetic energy of the tomato, added energy to it. So it did positive work to it. So then the net work would be 0. So it took away kinetic energy and then it added it back again. So that works for gravitational force. It also is true for spring force, okay? Because if you think of stretching the spring, okay, then if we pull that, we use a block to stretch the spring out, then technically the block is doing work on the spring. So that's like negative work. But then if we let go, then the spring does work on the block to speed it up. So that's positive work, okay? So those two are great examples of conservative forces. But it doesn't really matter how the object travels between 2 points, as long as all we care about are the starting and ending locations. So, for instance, you could look at this check for understanding. We can talk about it more. But think about the work being done here by gravity in particular. Okay, then we talk about non-conservative, or sometimes they're called dissipative forces. I'm not sure if I'm pronouncing that right. But those types of forces, the network is something other than zero. So a great example is friction or drag force, some other applied force. So in the case of friction, friction often does negative work and then takes away some kinetic energy that the system had. But you cannot reverse that process and get that energy, that kinetic energy back again. You can't. It's now left the system. This is like an infrared camera image of what happens when this car drifts, okay? And look at how hot that tire is and some of the chassis. That kinetic energy was transformed into thermal energy by the force of friction, and that thermal energy can't go be transformed back into kinetic again. So then that changes this check for understanding. If we cross out the word frictionless, if the pig is no longer greased, okay, then we would need to think about this answer differently. So we'll talk about this one more in class. So now if we go back to thinking about gravity, force of gravity, and spring forces, then we could start to think about instead of calculating work done on system, like on an object, then we could switch our focus and think about these forces doing really just being a transformation from one type of energy to another. If we include the objects in our system, so like expand our definition of what we are analyzing in a problem to include, if we're talking about gravity, then that's a force of planet Earth, say on a ball, or planet Earth on a person. So then we would need to analyze both planet Earth and the ball, okay, and put them both in the system. And then the force of gravity is an internal force. Then we can just analyze that as an internal force and really treat it like an exchange or transformation of energy instead of like a work being done on the system by an outside force. Same with spring. If we have a spring and a block, we could just consider the spring and the block together in the system, and then talk about how the spring potential energy is transferring to the block in its motion and speed in the form of kinetic. So let's talk about some equations then, right? We used to have a formula for work here, depending on, like, the work would be force times displacement, maybe, right? Force of gravity times displacement. Well, now we're transforming this into a potential energy formula, and we're going to use the variable capital U for potential energy. And so, again, we need to include planet Earth in our, like, system definition, okay? Because it must be there. Otherwise, we would say that, work is being done by outside forces. So, in order to say there are no outside forces acting on the system, we have to include planet Earth, like the whole planet, as a part of our system. Okay, that's a little odd. Okay, so we would have like this skater, say, and plus planet Earth in our system. And then we could explain that, like, if you set the person on the half pipe, I don't know how she got here, but if you set her up here, then her change in, she has gravitational potential energy because of her configuration relative to planet Earth. She is separated from planet Earth, and that force of gravity is going to want to pull her down. Okay, and so then we would say that potential energy is going to get transformed into kinetic as she goes down the half pipe, and then it's going to transform back into potential as she goes up the other side. And we can just analyze that transformation back and forth, okay? We'll take a look at that. We can watch that animation if you remind me in class. And then when we talk about elastic potential energy, we're talking about the potential energy that is stored when a spring block system or a mass on the end of the spring, okay, is stretched or compressed. So that has a certain zero level, okay? So the reference level is set where, the spring has zero potential energy when it's in its relaxed state. But then when you stretch it out or compress it by delta X, then it doesn't want to be like that, right? And then when you let go, some of that potential energy will be transformed into kinetic energy. So those are old formulas that we used to have for work. But now instead of saying, okay, well, I had to, where did the kinetic energy go? Well, it went into, doing work on something. Well, now instead of talking about it like that, if we include more in our system, we'll just talk about it as an energy transformation. So you have choices, okay, about what you include in your system and what you don't. And it's not that one way is right or wrong. It's just that you're going to choose a method that is easiest for and most efficient for your problem solving.